Hello friends, I am Rajneesh Kumar, working as an assistant professor in NIT Pharmacy Institute, Greater Noida. I am again in front of you with the next lecture of Pharmaceutical Organic Chemistry. Second subject code is BP301T. Okay, so in the previous lecture we are talking about the polynuclear hydrocarbons. So our focus was on phenanthrene and naphthalene. So in the previous lecture we have talked about synthesis, structure and usage of naphthalene and phenanthrene, and in the continuation of those lectures now I'm coming with the next topic. This is anthracene structure and synthesis. So in this lecture we will have the talk about the structure and synthesis of the anthracene. So as you know that anthracene, like phenanthrene, it is also having 3 benzene rings fused together. The only difference is in phenanthrene it is the 3 benzene rings are joined in the angular fashion, while in case of anthracene it is joined in the linear fashion. So both phenanthrene and anthracenes are the isomer of each other. Okay, so when we are going for the to know about the structure of anthracene, so as you can see that it is a tricyclic system. Tricyclic system means it is having 3 benzene rings which are joined with each other at ortho position in the linear fashion. Okay, so the molecule of anthracene is made of 3 benzene nuclei. You can see there in the structure. It is a colorless solid polycyclic aromatic hydrocarbons. Okay, so this is the structure of the anthracene. Okay, so when we are going for the number of the we go for the numbering for the carbon of the anthracene, then you can see there 1, 2, 3, 4, 5, 6, 7, 8. After numbering the terminal benzene rings, then we go for the middle ring, and we number them like 9 and 10. So when we compare the different carbons of the anthracene molecules, we found that the 1 carbon and 8 carbons are the equivalents, and these carbons are known as the alpha carbons. So 1, 4, 5 and 8, these 4 carbons are the equivalent and they are known as the alpha carbon, while 2, 3, 6 and 7 are equivalent and these are known as the beta carbon, while 9 and 10 carbons are again equivalent and these carbons are known as the gamma carbon. So as you can see in the structure, anthracene is having 3 equivalent carbon. Okay, now so when we are talking about the isolation of anthracene, so like phenanthrene, it is also isolated from the green oil fractions of the coal tar. Okay, so it is named as anthracene. So anthracene actually a Greek word which meaning a coal. So it is present in the coal tar to the extent of 0.3 to 3.5% in the green oil fraction of the coal tar. On distillation of coal tar, there is many fractions based on the temperature of the distillation process. So in green oil fractions, anthracene along with phenanthrene and other similar products will be there, which can isolate it very easily from there, and it is present 0.3 to 3.5% in the coal tar. So on distillation of tar, it passes over in the high boiling fraction anthracene oil. Okay, so that particular green oil fraction is also known as the anthracene oil fraction, because anthracene is a major product which is present in that particular fraction. So now coming to the structure of anthracene again. So after doing elemental analysis, mass spectroscopy, it is clearly found that the molecular formula of the anthracene is C14H10. The same molecular formula phenanthrene is also having. Because of that, the both are known as isomer of each other. So this molecular formula suggests that it is highly unsaturated product. Carbon numbers are more than the hydrogen. So it clearly indicates this is the very unsaturated product like benzene. Okay, and naphthalene, it can also be related. Okay. So, in benzene, if we join 4 carbon and 2 hydrogen, we are getting naphthalene. Again, if we add 4 more carbon and 2 more hydrogen, then we are getting anthracene, or you can see that phenanthrene is also there. Okay. So, we are getting anthracene by addition of certain fraction of carbon and hydrogen on the regular interval. So, you can say that anthracene is somewhere related to the naphthalene and in the benzene, and I already said that as per the formula it is clearly established that it is a highly unsaturated product. Okay. So, because it is related to the benzene, okay, it is related to benzene, and if we follow the Haworth rule, this is 4n plus 2 pi rule. So, it is having 14 pi bonds, sorry 7 pi bonds, means 14 pi electrons are there. Okay. When that particular value will be kept in the Haworth rule, then we are getting n is equal to 3, which is an integer number. It clearly again established that anthracene is an aromatic compounds like benzene or naphthalene. Okay. So, once it is established that it is a aromatic compounds, okay. So, like benzene and naphthalene, it prefer electrophilic substitution reaction when it undergoes for reactions, because the presence of electron cloud above and below of the plane of the anthracene. Why electron clouds are present? Because there are 14 carbon in the structure of anthracene, and each carbon is sp2 hybridized. sp2 hybridized means it is a planar molecule. Okay. So, each carbon is sp2 hybridized. Again, each carbon having 4 valency, 3 valency is satisfied with overlapping with 1 hydrogen and 2 neighboring carbon. Okay. 1 valency remains. Okay. That is unhybridized p orbital, which is perpendicular to the plane of the anthracene, and it is having unshared electron on that. Okay. So, each carbon having that p orbital perpendicular to the plane of anthracene, and that perpendicular p orbitals is overlapped with the neighboring orbital of the carbon. Okay. Because of that, electron cloud is generated along and below the plane of the anthracene. That electron cloud is responsible for its preference for the electrophilic substitution reaction. So, we know already that there are so many types of electrophilic substitution reaction like halogenation, like nitration, sulfonation, Friedel-Crafts acylation, and other. Okay. So, anthracene will undergo the electrophilic substitution reaction in the same manner as benzene or naphthalene undergo. Okay. So, now when we are talking about the structure of naphthalene, okay, anthracene. So, that structure again elemental analysis have done, mass spectroscopy have done, and both help us to establish the molecular formula. Now, we are again having some synthetic evidence. Okay. So, when we go for the bromination of anthracene, we are getting bromoanthracene. Okay. That bromoanthracene in the presence of potassium hydroxide gives hydroxyanthracene, which on oxidation in the presence of a strong oxidizing agent give orthobenzoyl benzoic acid and phthalic acid. So, phthalic acid and orthobenzoyl benzoic acid as a product will clearly indicate that anthracene is having at least 2 benzene ring as per this structure, or it is having 1 benzene ring having 2 carbon at ortho position. So, this is the clearly indication. Okay. Now, formation of orthobenzoyl benzoic acid from the previous reaction suggests that at least 2 benzene ring must be present in the anthracene molecule with the following structure. Okay. So, again if anthracene undergo oxidation, then we are getting anthraquinone, which on fusion with KOH, you have seen in the previous slide, gives 2 moles of benzoic acid. Formation of 2 molecules of benzoic acid from 1 molecule of anthraquinone further proves the presence of above skeletal structure for anthracene. So here you can see that the benzene ring, the anthracene structure is having 2 benzene rings which are joined together with carbon. Okay, ring. And now in this particular reaction, you can see that anthracene undergo the oxidation in presence of V2O5 and very high temperature. It gave anthraquinone, which on fusion with KOH gave 2 molecules of benzoic acid. It means if we are getting 2 molecules of benzoic acid, it means 2 benzene ring is certain in the structure of anthracene. It is confirmed now. Okay. Now the molecular formula as per this structure. Okay, the molecular formula is C14H9, but the molecular formula of anthracene is, again we have already found that C14H10. Okay, so for making that molecular formula, we just add 1 hydrogen and we close that ring here. Okay. So to fit in 1 hydrogen atom by considering the tetracovalency of carbon, the middle ring must be closed. Thus anthracene is assigned as a structure of 3 benzene ring fused together in linear pattern, as you can see in the structure. Okay. So I think it is clear in now in your minds. Then again there is some more evidence for the support of that particular structure. For example, anthracene add 7 molecules of hydrogen to give perhydroanthracene. So if it is adding 7 molecules of hydrogen, it means there are at least 7 pi bonds in the structure of anthracene. It clearly confirms. Okay. Again, the proposed structure of anthracene account for the formation of 3 monosubstituted and 15 disubstituted isomer of the anthracene, which again confirm the structure of anthracene like this. Okay. Now the most important part when we are talking about the structure of anthracene is the resonance concept. Okay. So we know that for creating resonating structure, we have to relocalize the pi bonds present in the structure. So after pi bonds delocalization, we are getting 4 resonating structure: 1, 2, 2, 4, 3rd and 4th. These are the resonating structure, and anthracene can be present like this. This is known as resonance hybrid. Okay. Okay. So the existence of resonance in anthracene is proved by the certain facts. Okay, like the resonance energy of anthracene is 351 kilojoule per mole. Okay, which is very higher. Okay, it again proved that it is very much stable compound because it is having very large amount of resonance energy. Okay, so anthracene is flat molecule because I have already told you that there is 14 carbons are there, and all 14 carbons are sp2 hybridized. Okay. Again, the double bond in between the carbons atom of the anthracene is not equivalent always. Okay. For example, if we going for the X-ray diffraction analysis, it proved that carbon bond in the anthracene are not equivalent. For example, C1 and C2 bonds has 3/4 double bond character, that is 1.37 angstroms, while C2 and C3 bonds have 1/4 double bond character, means it is having longer bond length, 1.42 angstrom. Okay. Now after talking about resonating structure of the anthracene, now I am coming to the molecular orbital structure of the anthracene. So I have already told you that there are 14 carbon in the anthracene, and each carbon is sp2 hybridized. Okay. So sp2 hybridized means it's a planar structure, and each carbon having 4 valency. Out of 4 valency, 3 valency like this. I am just drawing the structure. Okay, this is so एक कार्बन दो for example, if you are talking one of the carbon of the anthracene, so this is having 4 valency, so 3 valency is fulfilled by the overlapping of s orbital of hydrogen. So 1 valency is fulfilled here. Again the sp2 hybridized orbital 2 of the 3 is overlapped with the neighboring carbon. So 1, 2, 3 valency is fulfilled by the overlapping of the neighboring atoms. 1 valency which is remain is having p orbital which is perpendicular to the plane of the anthracene ring, and it is having unshared electron. Okay. So the whole molecule lies in one plane, and each carbon atom contain one unhybridized p orbital while lies perpendicular to the plane. The overlapping of these p orbitals can lead to the formation of pi electron cloud above and below the plane. Anthracene molecule has 14 pi electrons, so it always obey the Huckel's rule. Okay, so it is 14 pi electrons. When we put this value in the Huckel's rule, we will found that n is equal to 3, which is an integer number, which again confirm its aromaticity. Okay. So again you can see the structure of anthracene is this. It is confirmed by various analytical and synthetic evidence, and here you can see that this is a perpendicular p orbital on the carbon of anthracene, and these are overlapping laterally. Because of that, plane of the anthracene is having electron cloud above and below to it. Okay. Finally, the structure of anthracene can also be proved by the Haworth synthesis. So, like other polynuclear polynuclear aromatic hydrocarbons, anthracene can also be prepared by the Haworth synthesis. So, here we are using benzene ring as a starting material, and we reacted this benzene ring to the phthalic anhydride in the presence of Lewis acid like AlCl3. Friedel-Crafts reaction will be occurring, and we are getting orthobenzoyl benzoic acid. So, in this reaction, 1H, this bond will be broken, and this is going to this oxygen. Okay, and ये बॉन्ड यहाँ से टूट जाएगा. So or it will be attacking on that. So after that mechanism we are getting orthobenzoyl benzoic acid, which on reaction with the concentrated H2SO4. So we all know that concentrated H2SO4 is a very good dehydrating agent. So it will remove a water molecule from the orthobenzoyl benzoic acid. Cyclization occur, and we are getting 9,10-anthraquinone as a product. Again, for getting anthracene molecule, we have to reduce these two oxygen atom present on 9th and 10th position of the anthracene. So for that we go for that reduction in the presence of zinc dust. Okay, and we are getting anthracene as a product. Now I am coming to the synthetic part of the anthracene. So there are so many methods for the synthesis of anthracene. First of all, as you can see there, it can also one of the synthetic method we have discussed in Haworth synthesis. Okay, so where we are using benzene and phthalic anhydride. Okay, and Friedel-Crafts acylation reaction is going on in Haworth synthesis. Now again, Friedel-Crafts reaction can also be used if we condense 2 molecules of benzyl chloride here, CH2Cl and CH2 in the presence of Lewis acid like AlCl3. So what's happening actually? 2 molecule of HCl. Okay, this Cl and 1 H यहाँ से और 1 H यहाँ से, तो ये रिमूव हो जाएंगे. 2 molecule of HCl रिमूव हो जाएगा. We are getting 9,10 dihydroanthracene, and from here you can easily reduce oxidize the product in the presence of very good oxidizing agents. And so after oxidation, these 4 hydrogen atom will get removed, and we are getting anthracene as a product. So again, anthracene can also be prepared by the help of diol-salt reaction. So when we are talking about diol-salt reaction, we know that in diol-salt reaction we need 1 dienophile and 1 dienes. मतलब we need 1 dienes, एक dienes होनी चाहिए और एक dienes से प्यार करने वाला dienophile होना चाहिए. ठीक है. So as for the diol-salt reaction, you can see there is 1,3-butadiene. So we are having 1 dienes, and we are using this portion of 1,4-naphthaquinone as a dienophile. So what is happening actually here? Okay, like this. Okay, so 1,4-naphthaquinone when treated with the 1,3-butadiene, we are getting an adduct in that via diol-salt reaction, which on oxidation gave 9,10 anthraquinone, and after getting this product, it's very easy to obtain anthracene. We have just made this product undergo reduction reaction in the presence of zinc dust. When we heat this product, we are getting anthracene. Okay. Haworth synthesis we have already discussed about that. Again, we can discuss it. So in benzene we are using as a starting product, phthalic anhydride we are using. Then we use AlCl3, which is a Lewis acid. So in the presence of that, Friedel-Crafts acylation reaction is going on. Okay, so COR, this whole portion is R. So acylation is occurring. What is happening? Again I am telling you, this carbon is having 1 hydrogen. Okay, so again this bond will be broken. Okay, this bond will be broken. After that, this carbon will attack on that carbon. ये निकल जाएगा hydrogen, and this will be added to this oxygen. So because of that, we are getting orthobenzyl benzoic acid. Then again cyclization occur. How? One of the H of this ring and OH of that group will be removed. Will be removed as a water molecule. Cyclization occur, and we are getting 9,10 anthraquinone. After getting 9,10 anthraquinone, it is very easy to reduce these 2 oxygens. When we heat this product in zinc dust, we are getting anthracene as a product. Okay. So again, before concluding my lecture, I just want to focus on the structure of anthracene again. So I just want to show you like this, how electron cloud is formed. This is carbon, this is carbon, each carbon having 4 valency. Okay, so each carbon is sp2 hybridized. sp2 means planar. This carbon is sp2 hybridized, means anthracene is a planar molecule. Then suppose if I am talking about this carbon, so each carbon having 4 valency. Out of 4 valency, one bond is formed in between this carbon and this carbon. Second bond is formed between this carbon and this carbon, and the third bond will be formed in between this carbon and this carbon, and all these 3 bonds are sp2 hybridized because of the overlapping of sp2 hybridized orbital of the carbon. And this carbon hydrogen bond is formed because of the overlapping of s orbital of the hydrogen and sp2 hybridized orbital of the carbon. Okay. And one valency is fulfilled by like this. This is unhybridized p orbital. Okay, unhybridized p orbital, and this p orbital is having unpaired electron. Okay, so all the carbon is having same. Okay, and what's happening actually after that, these this unhybridized p orbital overlap laterally with each other. Okay, and because of that, a like this electron cloud is formed above and below of the plane of the benzene ring. Okay, that electron cloud is responsible for the preference of anthracene to the electrophilic substitution reaction. Okay, so this is all about the synthesis and structure of the anthracene. With this, I am concluding my lecture. Thank you.